question here is asking us to determine the force in each cable AB, AC and AD to support 17,500 Newton upwards force, and also given D to be 0.6 meter. We know that we're going to represent each one of those, since it's being given coordinates, we are going to represent them in a Cartesian form. So first thing, you do your sign convention. That's your sign convention, taking this direction to be positive, and for Y this is positive, same with Z, and if we're dealing with moments, anti-clockwise would be positive, and positive results are in, that means tension, and negative results means compression. So once we do that, we can draw our free body diagram. So drawing a free body diagram, in this case you can draw it, or in this case I will just I will take the one here in this diagram here. I will assume these are my forces just to save space and time, guys. So now this is my free body diagram. I will start to represent AB in a Cartesian form. So FAB, so I have FAB in a Cartesian form equal to the position vector AB divided by the magnitude of the position vector RAB. So to do that, then finding the position vector RAB equal, it's 1.2, as we can see that in the positive x-axis, 1.2i minus 0.9, which it goes 0.9 on the negative y-axis, 0.9j minus 3k. So many of you asked me, why is it negative on the z-axis? If you look here at A, the force is pulling upwards. However, this AB is pulling downwards. So downwards, the impact will be on the negative z-axis, because we are pulling with respect to AB is pulling downwards. If AB was to pull upwards, that will be positive z-axis. However, in this case it's going to be negative, because all of these cables pulling downwards, the impact on the z-axis is downwards, and that's why we're taking it to be negative. So now we get the magnitude. So the magnitude for RAB will equal to the square root of 1.2 square plus negative 0.9 square plus negative 3 square. All of this should equal to 3.25 roughly, the magnitude. So these of course are in meters in here. Now we can represent that force in here. FAB will be FB. So the force FAB, or in the cable FAB, will be FB. We have that magnitude here, 1.2 divided by 3.25 I minus 0.9 divided by 3.25 J minus 3 divided by 3.25 K. So this is how to represent the force in a Cartesian form. You can simplify this further. So RAB in this case will be this one here will equal to FB, and take this to be 0.35 I minus 0.269 J minus 0.896 K Newton. So this is for the force FAB. We'll do the same thing for FAC. So FAC equal to, we know it's the position vector of AC divided by the magnitude of that position vector. So to find the RAC, the position vector itself, this will equal, when we look here at this diagram for AC, so we move in here, if FD is 0.6, so 0.6 minus 1.2, it's 0.6 meters on the positive x-axis, and on the positive y-axis we move 0.9 meters, and again the z-axis is negative 3 meters because we are pulling downwards. Therefore this will be 0.9 6i, 0.6i, positive I, plus 0.9j minus 3k. And 3k, this is in meters. Now we find the magnitude of that position vector in there, which is 0.6 square plus 0.9 square plus negative 3 square. This all should equal to in this case 3.19. So now representing the force FAC, that cable, the force in that cable in a Cartesian form, we know it's the FC multiplied by 0.6 divided by 3.19i plus 0.9 divided by 3.19 j minus 3 divided by 3.19k. So this can be simplified. This one here, we can simplify it further. This will equal to FC. When you divide these two together, 0.188 I plus 0.282 0.282 j minus 0.94k. This is again in Newton. So this is for FAB AC. Then we will do the same thing for FAD. For FAD, again equal to the position vector of AD divided by the magnitude of that position vector AD. So in this case here, so RAD equal to when we look at this one here, at this on the diagram for AD, we can see that we move in negative 1.2 on the x-axis, and we subtract, this is 0.6 from the total 0.9, we will be left with 0.3 meters on the positive y-axis, and again negative 3 meters on the z-axis. So in this case, so that position here for the FAD will be negative FD itself. Sorry, so for the FRAD it's 1.2, negative 1. For FAD it's negative 1.2 I because it's on the negative x-axis, plus 0.3 j and minus 3k. So the magnitude for this will be taking the square root of 1.2 plus 0.3 square minus plus negative 3 square, and in this case this will equal 3.25. So now representing the FAD in a Cartesian form will equal to the FD itself. So it's a negative 1.2 divided by 3.25i plus 0.3 divided by 3.25j minus 3 divided by 3.25k. So this is for FD. Finally, these are all the forces acting there to represent them in a Cartesian form. So now we can start applying our equilibrium equations. So equations of equilibriums, sum of the forces on the x-axis should equal to 0. From here we can say FAB on the x-axis plus FAC on the x-axis plus FAB on the x-axis, and also we have the force applied upwards straight on the z-axis, it's 0. So AB, AC, AD, sorry guys, this is FAD. There it doesn't have anything on the x-axis. All of these should equal to 0. Just plug in these values that we found recently. That will be 0.358 FB, 358 FB plus in this case 0.188 FC and minus FD, and for the x-axis for the FD it's a negative 0.923 FD. All of this should equal to 0, and let's number this our first equations in there. Then we take sum of the forces on the y-axis, again should equal to 0. From here we know that FAB on the y-axis plus FAC on the y-axis plus FAD on the y-axis, all of them should equal to 0. Plug in all of these number. We have this is negative 0.269 FB, and the other one plus 0.282 plus 0.28282 0.282 FC, and finally for this one here 0.92 FD plus 0.92 FD, all of them should equal to 0. Let's take this to be our second equation. We do the same thing for sum of the forces on the z-axis should equal to 0. FAB on the z-axis plus FAC on the z-axis plus FAD on the z-axis, plus of course we have positive 17,500 Newton straight upwards on the z-axis as well. They all should equal to 0. So simplify this a bit further. These values in here, it's first one in here FAB on that. If you take this to the other side, that can be positive 0.896. Guys, it is negative, however I'm taking it to the other side so that just saving time. It's 0.896 FB. Again, this one is negative, but when you take it to the other side will be 0.94 FC. Again, this one is negative, but taking it to the other side is going to be 0.923 FD. All of this should equal, again taking this to the other side, will be 17,500 Newton. This is our third equation. Now we have three equations, so solving simultaneous equation. So solving for three simultaneous equation. Equations. Plug these in your calculators and you should get the values for FB and FC, FD. Once you put these all in your calculator, just solve them simultaneously. This is how you solve these types of questions. See you guys in the next video.